I'm Yusin from the National Research Foundation, and I will be your MC for this afternoon. Without further ado, we will now dive right back into the program. Our first speaker this afternoon is Prof Adi Shamir. His talk is on a new theory of adversarial examples in machine learning. The Q&A session will be moderated by Prof Cao Debin from the Singapore Management University. Prof Shamir, please.
So I'm going to talk about some security issues of machine learning. As you see, I'm switching to the hot new fashionable topic of machine learning, but still starting from my base, looking at security issues. And it's clear to all of us now that the introduction of deep neural networks about 10 years ago had profound impact, lots of applications. But there are several remaining major problems in the field. First of all, there is the issue of explainability. How do the deep neural networks learn to distinguish between two classes? They are successful. You give them examples of the two classes, and they will tell you 99.9% of the time the correct answer. But how do they distinguish between cats and dogs? We have no idea. So that's problem number one. Problem number two is how do they learn from 1,000 images of particular cats to recognize other kinds of cats, which as an image look totally different. The cat is standing or sitting or lying in a different pose, in a different part of the image. So no two images that we gave as training examples of cats are going to look alike. How can the network extract what is common to the 1,000 images and decide how to generalize to new kinds of images which it never saw before? And the third major mystery is the issue of adversarial examples, which was briefly mentioned in Les Valiant's talk this morning. They seem to be sensitive, extremely sensitive to tiny changes in the input. And if you have never seen an adversarial example before, I'm going to show you now, and it will blow your mind off. So here is an example of an adversarial example. The picture on the left is recognized with 88% confidence level that this is a particular kind of cat, tabby cat. You make an imperceptible change to the image. I don't think any one of you sees any difference between the left image and the right image. And with 99% confidence level, the best available deep neural network, which does a great job at recognizing cats, will say this is guacamole. It is absolutely sure. How come successful deep neural networks make such stupid mistakes that even, a 2-year-old baby will never do? So here's another famous example in this field. By the way, the phenomenon was invented about 10 years ago by Segedi and Biggio independently. And it has many security implications. For example, people show that if you take a road sign, say a stop sign, and you want to confuse a Tesla auto-driving car, you just put a few, 2 or 3 stickers, black and white stickers, small ones in particularly chosen locations on the traffic sign, and suddenly it will recognize it as 45 mile per hour zone, and it will not stop at that intersection. So it can be really dangerous. So the next example is proof that pigs can fly. This is an image which is correctly recognized as a pig. What you see in the middle is the kind of change, perturbation you make to the image. And this is actually a highly exaggerated change. You multiply this noise pattern by 0.005, so it becomes essentially flat gray level image. You don't see the pattern in it. This pattern has to be very carefully chosen, because if you choose another pattern, it will say that this pig is not an airliner, but it is a horse, or it is a fire truck, or it is a bicycle. choose a particular pattern, and it will change its mind to any other class. How come deep neural networks are so stupid? So in spite of a lot of effort over the last 10 years, no one had come up with a really good explanation for what is going on. I'll try to give you an answer that hopefully will convince you. Here are some recent quotes from the top experts in the field. Nicholas Carlini, who published some of the best papers on adversarial attacks and defenses, says, I'm in a world where I don't know what are these adversarial examples. And Dimitris Tsipras, who did his PhD at MIT, said something similar. The various explanations you can find in the literature are very confusing and contradictory. For example, one person had published a paper in which he said that the reason adversarial examples exist is due to the highly nonlinear nature of deep neural networks. Not that it explains much, but a year later he published a paper in which he said adversarial examples exist due to the local linearity of deep neural network. So just the opposite of what he said a year earlier. Of course, in order to decide what is the real explanation, you ask ChatGPT, right? So here is the answer you got from ChatGPT. I asked it a few days ago. It's ChatGPT 4.0, the best we have at the moment. Why are DNNs so vulnerable to adversarial examples? And the answer was, DNNs are particularly vulnerable to adversarial examples because they are highly nonlinear and have many parameters. Does it explain anything? Not. Then it says something totally stupid. Adversarial examples can be seen as a form of overfitting, where the model has learned to classify both the training data and the adversarial examples, but fails to generalize to new examples. Totally wrong, because it didn't learn, it was never shown examples of adversarial examples during its training. So it didn't learn how to recognize them. It's an artifact and not something that it learned as part of the training process. And also it fails to generalize to new examples, again wrong, because every other cat or a pig that had not been adversarially modified will be recognized correctly. So it does generalize very well, but it is still extremely sensitive to those small changes. So you all agree with me that even experts like ChatGPT don't understand the phenomenon. Okay, when you go to Machine Learning 101 at a major university, here is the mental image that the teacher will try to instill in your mind. This is one of the most misleading pictures I've ever seen. It directs you to think about the problem in completely the wrong way. I'll give you a different mental image soon. So they say, okay, you have a bunch of cats, red cluster of cats, another cluster of cats, and here is a cluster of guacamoles and another cluster of guacamoles. And what does, these are, every point in this space, this is the input space, every point in the space is a complete image of a cat. So here is one example of a cat, and here is another example of a cat, maybe a cat of particular breed, and this is a cluster of cats of another breed, and so on. And when the deep neural network sees many examples and is taught how to distinguish between the two classes, and by the way, I'll concentrate in my talk only about two-class classifiers. Otherwise, it becomes more complicated to think about it. So there is cats and guacamoles, that's all. So the goal of the training is to learn some kind of decision boundary so that it divides the space into regions. Everything on one side of this decision boundary is going to be called by the network as a cat. So the cats are going to be recognized correctly, but also those points which don't look like a cat are going to be recognized as cats if you'll happen to give it these training examples. And everything here and here is on the right side of the decision boundary. So it is going to be classified as guacamole. And the decision boundary can be viewed as the collection of points at which the network thinks 50%, it's a 50% chance to be a cat and 50% chance to be guacamole. It is equally undecided between the two possibilities. And in addition to this decision boundary, you can also think about additional lines. So this is the line where you think with 51% confidence level that it was a cat, and 49% confidence level it was guacamole, and here it's the opposite side. So you start getting things which look like a topographic map with height lines, okay? So as you get further and further in this direction, you become more and more confident that it was a cat, and you place all the training examples to be above the 90% confidence level of being of the correct class. So I hope it is clear what is the mental image which is usually taught about how networks are trained, and now what is the meaning of adversarial examples. So adversarial examples, you start from an image of a cat, and you perturb it so that it will move in the direction of the decision boundary. It will cross the decision boundary to the other side, and actually it will go so far away that it will actually, while these are only 90% sure that it was guacamole, you go far away so that it will be 99% sure that it was guacamole, okay? So when one of the co-authors of the original paper about adversarial examples from 2013 was asked in a public lecture, what is the meaning of the perturbation, this crazy pattern, random looking pattern, which moves you from the cat to something that looks like a cat but is recognized as guacamole? He says, those directions are pointing from one class centroid to another class centroid. But if you think about it, the pig, which was changed into an airliner, you had to put something which characterizes an airliner. But did you see in the random pattern either wings or engines or a tail or anything that reminds you of being an airliner? No, it was just random looking pattern. So what does it mean that you are pointing from a centroid of cats to a centroid of guacamoles? If true, the perturbation should have increased a lot the amount of greenishness, for example, in the image to make it look more like guacamole. Okay, so this clearly doesn't make any sense, and you can ask yourself all kinds of questions. What's special about those particular perturbations which make a cat into guacamole? Certainly it's not a normal cat, even though to a human it looks like a cat. How can it be that next to any cat image, I can find with one perturbation something that still looks exactly the same, a cat, but it is recognized as a car? Another perturbation will move you to an airplane, to a boat, to a horse, frog. You can change it to thousands of other classes. Why are the adversarial examples so close to the original images? You don't go all the way, as in the mental image, to the other side of the decision boundary and even beyond the given examples to the 99% confidence level. And why don't the adversarial perturbations resemble the target class? Okay, so these are the big questions I'm going to try to answer today. So the new theory analyzes the geometry of adversarial examples, and basically I'm going to look at high-dimensional domains where it is known that natural images occupy only a tiny sub-regions within the input space. If I pick a random point in the input space, it is going to look like random noise. Images have all kinds of natural images have all kinds of characteristics. For example, they are locally smooth, but occasionally, as I move around among the pixels of the image, I cross a boundary, and then there is a sudden change in the color or in the light intensity. But overall, it's fairly smooth. So we call such a description of where natural images lie a manifold because it is locally looking like a linear subspace of much lower dimension, but globally it bends around, so it's not completely flat. Think about the surface of a ball in n-dimensional space. So looked under a microscope, the surface of the ball looks very flat, but overall, globally, it bends around. So that's the definition intuitive definition of a manifold, mathematical manifold. So I claim that because natural images are lying on a small dimensional manifold, while the deep neural network is taught to construct a decision boundary which is everywhere dividing the high dimensional space into two regions, one region which is called a cat and one region which is called guacamole. This is the source, and I'll show you in a moment what is the process that creates those adversarial examples. Okay, so first of all, we have, in order to run the experiments I'm going to describe to you, we have to understand how do we actually construct and experiment on the manifold of natural images. So the easiest way to do it is to compress images into much smaller number of parameters. So this is called an autoencoder. It is a deep neural network which gets the n-dimensional input. So I assume that I have n pixels. Each pixel is described by a number between 0 and 1. So I'm working within an input space which is the 0, 1 to the power n space. And the deep neural network has many layers, and it compresses the input image to a small k-dimensional latent space, which tries to describe as best as it could to the input. What forces it to describe, to compress it into the k-dimensional intermediate description, because then you have a decompressor which generates an n-dimensional output. So you start from such an architecture of a deep neural network, and you train it with many, many examples of natural images. It doesn't try to classify them, but you penalize the network for having an output which is different from the input. You are steering it towards generating an output which is as close to the input as possible. And after you give it 1 billion examples of natural images, it learns how to compress it by, for example, eliminating local noisy regions, smoothing jagged lines, etc. And actually, these autoencoders are doing a great job. Here is an example. You start from such an image. You compress the image by a factor of 42, in this particular case. That's how much n is bigger than the bottleneck k in the middle. And after the compression and decompression, you get something which looks very similar to the original image. So after the training, the autoencoder learns how to represent each image within a small number of parameters, 1/42 size. And then, once we trained the network, we suddenly have a local description of the manifold. What does it mean? You look only at the decompressor. If I'm taking my cat image as an input, it moves me to a point in the latent space, in the much smaller k-dimensional subspace. And then I know how to represent this cat image by only a small number of parameters. As I'm varying, for example, the first of the k parameters, making it slightly bigger or slightly smaller, I'm moving in the output space here in a particular direction. If I'm changing only the second representation parameter, I'm moving in another direction in the output space. If I'm looking at all the k of them, I'm getting k directions, and the linear space for which these k directions are the basis of describe the local linear structure of the manifold of natural images. If you didn't get all the details here, it's not important. You just have to understand that we have a very good way how to find in the vicinity of each image all the ways how I can move to nearby points, walking only on the subspace of natural images. Okay. Now let's go back to our cats and guacamoles. How would you distinguish, if the only thing you have to distinguish between are, given an image, is it a cat or guacamole? So you notice from experience that there are very few green cats, right? So if the image is mostly green, you you say it's guacamole. If it's mostly gray or white or black, not green, you say it's guacamole. Very easy decision. So here is the parameter space, one-dimensional parameter space. This side it's greenish, this side it's grayish, and here is an example of a cat, here is an example of guacamole. How are you going to distinguish between them? The decision boundary is a point which is probably about halfway between the two training examples, and you say anything which is more gray than this intermediate point, you call it a cat. That's the output you provide. Anything which is more green, then you say this is guacamole. Very natural, that's what you expect. Now, we are adding another complication. The one-dimensional line of images, which is based only on how greenish the image was, let's add additional parameters which are not usable at all in distinguishing between cats and guacamoles. For example, it could be whether the top left pixel in the image is brighter or darker than usual. You agree that this top left corner probably has nothing to do with the decision whether it was guacamole or a cat. But it is a parameter. The images have multiple parameters. You have n-dimensional space, you have n parameters, and the decision boundary has to be n-1 dimensional dividing region, because it must separate the space in a way that any way of going from cats to guacamoles will pass through the decision boundary. You cannot go smoothly from 90% cat into 90% guacamole without going along the way through 50% indecision point. Okay? So what do you expect in a two-dimensional input space where only one of them matters and the other one doesn't matter? How do you expect the decision boundary to look like? You say, okay, because the vertical direction doesn't matter, I'll have a vertical decision boundary. It is n-1 dimensional, namely one-dimensional line. Everything on the left side is called the cat, everything on the right side is called guacamole, right? Wrong. That's not what's happening. So remember that other decision boundaries are also possible, and they'll do exactly the same job as the original vertical decision boundary as far as points on the low-dimensional manifold of natural images is concerned. Any kind of diagonal line like this will also separate all the training examples correctly to the left and to the right. But even this is not what's going to happen in reality. What I'm going to describe to you is the new mental image. It doesn't quite happen in the trivial example of just 2 points, but it happens in the normal cases, which I'll describe in a moment. So here is the new decision boundary, which my new theory suggests. And by the way, when I say mine, it's a joint work with 2 of my students, Odelia Melamed and Ben Shmuel. And here is the decision boundary. So the decision boundary kind of follows the manifold of natural images, except that it creates what I call dimples around the examples of cats and guacamoles. So it's a one-dimensional decision boundary in the two-dimensional space. The network is going to call everything above this decision boundary a cat. Everything below the decision boundary is going to be called a guacamole. And notice that it uses directions, it uses dimensions which are unimportant in reality in order to distinguish between cats and guacamoles. Instead, it is using them in order to make its life easier, and I'll explain in a moment why. It is using the additional available dimensions, and there are a huge number of them because I compressed my image by a factor of, say, 42. So about 98% of the dimensions are available to me even though they don't make any difference. But I'm dividing the whole input space in its full glory with all the original n parameters. I'm not only dividing the manifold into region, I'm also dividing every input point, whether it makes sense or doesn't make sense. Okay, let's, in order to sharpen our intuition, let's go to two-dimensional manifold in a three-dimensional space. So I have 4 clusters of cats and guacamoles, and the only thing that matters to decide between cats and the guacamoles is their position on the two-dimensional surface. But there are additional dimensions, which any compression algorithm will throw away, and the decision boundary which will be created is actually looking like this. So you have a decision boundary which follows the manifold of natural images, except that sometimes it slightly dips below and sometimes it slightly dips above. This is something that people haven't noticed because they never experimented in actually looking at how decision boundaries evolve during the training process. So let me show you now some videos where we ran actual experiments trying to see what do decision boundary looks like. Are they the mental image we had before of the two-dimensional space, one side cats, the other side guacamoles? No, there is additional dimensions coming out of the screen which we didn't think about as being useful, but the deep neural network actually uses in order to build a decision boundary. So let's, our theory claims that actually the process of training deep neural network consists of two steps. One is to cling quickly. In the first few times you go through the training examples to discover and cling to the decision boundary, to the image manifold. And then over a much longer period of time, you are building those dimples that will give you the correct label for the training examples. So here are examples. So this is a sequence of snapshots. Here are the training examples. They are all on one line. The only thing that matters is the left to right position on this line. So I have the red cats and the blue guacamoles, and my original random initialization of the network doesn't understand anything about cats and guacamoles, so it is passing here. After 10 epochs, going through the data 10 times in the training, it starts moving closer, and here 20 epochs and 30 epochs, and eventually you see this dimpled structure. Here is an actual video of a horizontal line or a diagonal line, how during the training, the position of the decision boundary evolves. And you see the network struggling to put, after it quickly clung to it, to the general direction, now it starts moving things around, fine-tuning them so that all the red points are going to be on one side and all the blue points are going to be on the other side. Okay, here is an example in 3 dimensions. I have a checkerboard pattern of class 1 and class 2, red and blue. After the training, you get this pattern in which you have the upward bumps and the downward bumps, which I promised. These are actual experiments, not my mental image. If you try to train your network on this set of examples, that's what you're going to get. Here are videos showing the process going from the original random initialization, where there was nothing correct about the decision boundary. Think about the decision boundary. We color-coded it, so it will look like a topographic surface where the higher regions are colored with brown, and the lower regions are going through the red, and then the yellow, and then the green, and then the blue. So here is a video showing the evolution. Sorry, here. It clings and it dimples. Okay? Look at it once more. Exactly as the theory suggested. Okay. Here is an example of a one-dimensional line in a three-dimensional space, and again, the surface has to divide the whole three-dimensional region into 2 parts. So it is a 2-dimensional surface. It's not penalized for how it is behaved away from the training examples, But near the training examples, you see that it goes up and down and dimples as it should be according to the theory. Now I'll explain to you what is the logic behind this process of clinging and dimpling. Suppose that you have your training examples in the one-dimensional line. The whole space is two-dimensional, and the initial random initialization of the network is going to give you this crazy pattern which doesn't classify correctly. So what are the pressures on the decision boundary created by the training? This wants to be below the decision boundary. It is already below, so it's very happy. It is not applying any pressure to move this decision boundary upward or downwards. These cats are very unhappy with where the decision boundary is located with respect to them. Why? Because they want the decision boundary to go underneath. Cats should be above the decision boundary. So they apply a lot of pressure for the decision boundary to go down and to bypass them below. Same here. How about the guacamoles here? They are unhappy because they want to be below the decision boundary. They cannot move themselves, but they will try to change the parameters so that the decision boundary will go above them. If you look at the arrows of where the pressures are, they are always going to point in the direction of the image manifold. So this is not going to apply any pressure. The pressure is only to get closer. And that's why you have the fast clinging. You are moving towards the image manifold. And now we get to the issue of adversarial examples. What is an adversarial example? At any intermediate point during the training, I'm drawing the direction where if I froze the deep neural network at this stage, in which direction I would like to go in order to increase maximally the guacamole-ness of the current image of a cat. So you see that I'm always trying to be perpendicularly to the decision boundary or to the height lines. That's the fastest way to move away from my current decision towards the opposite decision. And because I said that the decision boundary is almost flat, just undulating slightly, the adversarial direction, the perturbation, has nothing to do with moving horizontally in the image manifold, trying to increase greenness or make the image more smooth or anything. I'm moving in totally other directions, which are totally irrelevant to the decision. And this is the reason why you don't see pattern of wings or engines in the perturbation. You are moving in the network uses the additional useless dimensions in order to make its process of building a good decision boundary easier. Okay, I'm running out of time. Here is another example in high dimensions in CFAR 10, for those of you who know it, of what is the average distance. This is the distance. This is the epoch. How many times I went through the input examples during the training. The clinging process brings the decision boundary very close and very rapidly towards the examples. So you see that the distance, average distance between the decision boundary and the given examples rapidly drops. This is the point at which I almost reached the decision boundary almost reached the image manifold. And then it slowly increases because I'm building those bumps up and down, and that's exactly what I expected from the theory. Okay, I'll skip this. It's another example of produced not by me, showing that there are two phases in the process of learning, but people hadn't noticed, hadn't thought much about its effect. So the claim is that the training tends to create large gradients. What does it mean to have a large gradient? The gradient is, if I go in that perpendicular direction, how fast do I change my decision? So I could have either large gradients, and then I'll have to go very, very gently, slightly above and slightly below the cats and the guacamoles in order to reach the 99% confidence level. Having low gradients means that I have to go deep under the cats and very high above the guacamoles in order to change my the network in order to be at 99% confidence level of being a cat, it will have to be way above the decision boundary. So the decision boundary will have to dip very low. So networks don't like to make such big changes in direction. They prefer to very gently undulate above and below the training examples, but this implies having large gradients, which is the reason why you have short distances from the given examples. Okay, so let's skip this. So suddenly everything becomes intuitively obvious. So what are those adversarial examples? When I have a cat and I want to change it into guacamole, I don't add greenishness. I don't make the image smoother. I go in crazy new directions. Why do I go a short distance away? Because the network wanted to have these large gradients in order to have very smooth, varying kind of decision boundary, undulating above and below the training examples. So that's why having large gradients, I have to move only a small distance in order to completely change my mind. Why don't you see the patterns of the target class? Because you're not moving towards the other class, you're moving in a perpendicular direction. So everything becomes intuitively obvious. I'm running out of time, so I'll just try to summarize. Comparing the two mental images. In the old mental image, the way you created adversarial examples, as a good fellow mentioned in his televised lecture, he said that you are moving from a cluster of cats in the direction of a centroid of guacamoles. In the new theory, you move in a perpendicular direction. Nothing to do with trying to imitate the properties of the target class. How, in the old mental image, the two-dimensional one that I showed at the beginning, how do you create adversarial examples? You go all the way to cross the faraway decision boundary and then go a long way beyond it in order to move in the direction of actual guacamoles, which are mostly green and therefore very different than the class I started with, which is mostly gray. The new mental image, I move a tiny distance. And in the old mental image, I was moving in the direction of real cats, real guacamoles. And the new one, I create pseudo-images which have nothing to do with the properties of guacamoles. Okay, there are many other things which are explained by the theory, but I'm running out of time. So I'll skip it. Let's see if there's anything else I wanted to say. I'll finish with one mystery which is solved by the new theory. Several years ago, a group from MIT published a very surprising result. Namely, they took cats and they made those perturbations, adversarial perturbations, which made all the examples of cats into something that the network thought were guacamoles. And then they took a bunch of guacamoles, made the perturbations that make the network think that they are cats. And now they took only the adversarial examples, not the original ones. So the new training examples contains only things that look like cats, but are labeled as guacamoles, and only things which look to a human person like guacamoles, but all of them are called cats. And you train a new network on the examples with the incorrect labels that I just mentioned. What would you expect the new network to do when presented with a real image of a cat? Because it never saw anything that looks like a cat being called a cat, you expect that a real cat will be classified as guacamole. No, the new network will recognize real images of cats as real, it will give it the label of cats, and real images of guacamoles, it will say they are guacamoles, even though throughout the training, all cat-looking images called guacamoles and vice versa. This is perfectly explained by the new theory, but I don't have time to go over the explanation. That's the explanation. Okay, I'll skip it, get to the conclusions. So I presented a new theory. It really explains in a very good way, the mysteries of adversarial examples. I think that not everyone in the field accepts this theory. Many people, as you saw, had their own pet theories, but I believe that this is the first time that you get a feeling for what does it mean to move in an adversarial direction without increasing any property that is associated with the target class. Thank you.
Can I put you over here? Take a seat. All right, thank you very much for the very interesting talk. We learned not only about the severe consequences of these adversarial examples, but also an intuitive explanation as to what is actually happening. So with that, I think we will have time to take maybe like 1 or 2 questions.
Okay.
Go ahead.
Hi, sorry, I don't do machine learning, so I just have a very simple question. So you mentioned that I get that the forces causes the surface to cling onto those nodes.
Yes.
But isn't it just because you order them in this alternating fashion? So
no, it doesn't matter because if I put several red points, all of them are going to try to move the decision boundary simultaneously below them. It will not dimple underneath and then go back to a normal and then dimple a second time. It will kind of create one big dimple underneath all 3 points which are adjacent to each other. So the alternating order doesn't matter much.
I see, thank you.
All right, maybe another question?
Yes, okay, I'm gonna ask about something else, large language modeling.
Yes.
So large language model feed a lot of information to it. So once it got fed with all information, now we can see ChatGPT and all of that. It's really doing great. But what happens when ChatGPT starts to learn from the content that it generates itself? Because now most of us as a student and all of that, we use ChatGPT and all of that. So the internet is full of ChatGPT content created. So the machine gonna eat itself somehow, if the impression is correct, and somehow the content creation becomes more towards machine, like not really generative model based on real data. So what do you think about that?
It's clear that this process of self-enhancement could create a situation in which one version of ChatGPT will start believing that a particular cat is God, and it will start writing about how this cat created the world. And of course, this will be picked up by the next generation of ChatGPT, and it will produce even more content talking about the virtues of this God cat, and it will just propagate, and the whole ChatGPT will move in the direction of cats being gods. So I think that we have to be very careful at learning from outputs which had been generated by ChatGPT. You will get a very strong movement in a crazy direction, which is hard to predict. Just you start creating a trend and you self-enhance it in next generations. So it's a problem we have to consider.
Okay, to continue about that, because this is what happened during my PhD. I built a model and all of that. So I had the idea to feed my model what I generated, and it goes crazy.
Exactly.
And the thing is, how can we prevent in the future? Because reverse engineering doesn't work at generative models. So how can the people working on all generative models like ChatGPT or these things, how can they differentiate what content is being created?
So due to totally other reasons, namely privacy issues and preventing kind of fake news, etc., there are proposals that everything produced by generative models, whether ChatGPT or images, etc., which had been artificially generated, will be marked as such. So you will not be able to put on the internet anything generated by ChatGPT, which is not marked as this was generated by ChatGPT. So then, if this is implemented and followed, it will be very easy to continue to train only on human-produced content.
Great. Thank you very much for the questions and the explanation. All right, I'm afraid that we are out of time, so we will not be able to take more questions. But I think we have a very interesting session today. We learned about how machine learning works. We also, hopefully, with this particular lecture, it triggers more thoughts into the explainability, as well as how we can actually think about the scene, behind the scene as to how adversarial machine learning actually works. Right. Let's put our hands together and thank Professor Shamir again.
Thanks.
Thank you.